What if I told you the universe's greatest mysteries might be hiding in the tiniest building blocks of existence? Long before planets, stars, or even galaxies took shape, something extraordinary was happening in the cosmic darkness. A silent dance of atoms, colliding and combining, giving birth to the very first complex molecules. These fragile, ancient structures weren't just cosmic accidents. They were the blueprints for everything that followed, the hidden code that set the stage for life itself. And today, we're diving deep into 30 mind-bending theories about how these molecules came to be, why they matter, and what they reveal about our origins. Picture this, a universe so young it hadn't even lit its first stars. No light, no warmth, just a vast, swirling sea of raw ingredients. Yet, against all odds, atoms began to bond in ways no one thought possible. Hydrogen, carbon, oxygen, these simple pieces started forming chains, rings, and even the precursors to DNA. How? That's the question that's haunted scientists for decades. Some believe cosmic rays acted as matchmakers, zipping through space and sparking chemical reactions. Others argue that the crushing pressures inside interstellar clouds forged these molecules like a celestial blacksmith. And then there are the wilder ideas like molecules hitching rides on comets or even forming in the hearts of dying stars. But here's what's truly astonishing: these molecules didn't just vanish. They're still out there, frozen in time, drifting between the stars or locked inside ancient meteorites. They're cosmic time capsules, whispering secrets about how the universe went from a lifeless void to a place teeming with complexity. And that's why this story isn't just about chemistry, it's about us. Because every atom in your body, every breath you take, can be traced back to those first fragile bonds. So, if you've ever looked up at the night sky and wondered how it all began, you're about to uncover some of the most thrilling clues science has ever found. Ready to explore? Let's go! The first whispers of complexity in our universe might have come from something as ordinary as water. Picture Earth 4.5 billion years ago, a violent, churning place with volcanoes spewing gases, lightning splitting the sky, and vast, shallow oceans simmering under a young sun. In those waters, scientists believe, floated a cocktail of simple molecules: ammonia, methane, hydrogen, like ingredients waiting for a recipe. This is the heart of the primordial soup hypothesis, the idea that life's building blocks first assembled in Earth's ancient oceans. The theory gained legs in 1953 when Stanley Miller and Harold Urey recreated those conditions in a lab. Their famous experiment zapped a mix of gases with electricity, mimicking lightning, and within days the flask was swimming with amino acids, the very stuff proteins are made of. It was a revelation. The universe's first complex molecules might have cooked up in puddles, but here's the twist. While Miller and Urey's experiment showed how simple molecules could combine, not everyone's convinced this was the universe's only kitchen. For one, Earth's early atmosphere might not have matched their gas mix. Some argue volcanoes pumped out more carbon dioxide, less methane, which changes the chemistry entirely. Others point out that amino acids are just one piece of the puzzle. They don't explain how these molecules linked into chains, or why some arrangements led to life while others fizzled out. Then there's the bigger question: was Earth even the first chef? Space is littered with complex molecules, from formaldehyde in distant clouds to sugars on comets. Maybe the soup wasn't just simmering here, maybe the universe served it cold, delivering pre-made ingredients via asteroids. The primordial soup hypothesis opened the door, but now we're realizing the kitchen might be cosmic. And that changes everything, because if complex molecules could form both in Earth's oceans and in the void between stars, then the recipe for life isn't rare, it's written into the fabric of reality. While the primordial soup theory paints a vivid picture of life's ingredients brewing in ancient oceans, there's another, far more extreme kitchen where complex molecules might have cooked up: hydrothermal vents. Imagine plunging into the crushing depths of the early Earth's oceans, where towering chimneys of rock spew superheated water loaded with minerals into the icy darkness. These underwater geysers, hotter than 300 degrees Celsius, seem like the last place you'd expect delicate chemistry to thrive. Yet, some scientists believe these violent, mineral-rich environments were perfect laboratories for assembling life's first building blocks. The key lies in the vents' unique structure. Their porous rock surfaces act like microscopic scaffolds, giving molecules a place to cling and interact. The heat provides energy, while the steep temperature gradients scalding at the vent's mouth, freezing just inches away, create natural convection currents, constantly shuffling chemicals together. And unlike the soup theory, which relies on random lightning strikes, hydrothermal vents offer a steady, relentless energy source. Minerals like iron and nickel might have acted as catalysts, speeding up reactions that would take eons elsewhere. Picture a molecular assembly line, with each vent's nooks and crannies guiding simple compounds into more complex structures. This idea gained traction when researchers found vents teeming with microbes, today organisms that thrive without sunlight, surviving on chemicals alone. Could their ancestors have been the first to stitch together complex molecules? The vents also solve a puzzle the soup theory struggles with: protection. Earth's surface was bombarded by ultraviolet radiation and asteroids early on, but deep underwater, molecules would have been shielded, free to evolve without constant disruption. But here's where the debate gets spicy. Critics point out that while vents excel at creating small organic molecules, they might not be great at forming long chains like proteins or RNA. The same heat that drives reactions can also break fragile bonds. Plus, the acidic conditions near some vents could hinder certain chemical steps. This isn't to say vents didn't play a role, just that they might have been one chapter in a much longer story, working alongside other environments like tidal pools or even comet impact. The beauty of this theory, it expands the possibilities. If life's blueprint can emerge in such extreme places, then maybe it's not just Earth's oceans we should be searching, but the hidden seas of Europa or Enceladus, where similar vents might still be bubbling away. The universe's first complex molecules could have been forged in pressure cookers, not gentle soups, rewriting our ideas of where and how life truly begins. Now let's step outside Earth entirely, because what if the universe's first complex molecules didn't form here at all? Imagine them hitching a ride on comets or tucked inside meteorites, raining down onto our young planet like cosmic care packages. This is the wild premise of Panspermia, the idea that life's ingredients were delivered from space, and the evidence isn't just speculation, it's written in the rocks. Take the Murchison meteorite, a rusty space rock that fell in Australia in 1969. When scientists cracked it open, they found over 90 different amino acids inside, some of which are identical to the ones in your DNA. How did they get there? The answer might lie in the icy depths of space itself. Far from stars, in the frigid voids between solar systems, simple molecules like water and carbon monoxide freeze onto dust grains, forming cosmic ice rinks. When hit by starlight or cosmic rays, these ices can rearrange into complex organic compounds, amino acids, sugars, even the building blocks of RNA. Over millions of years, these dust grains clump into comets, which then barrel into planets like ours, seeding them with pre-made chemistry. It's like the universe had a molecular delivery service long before FedEx. But Panspermia doesn't just shift the location of life's kitchen, it changes the timeline. If complex molecules were already floating in space before Earth even formed, then the recipe for life might be far older than we thought. Some researchers argue this solves a major puzzle: how life emerged so quickly once Earth cooled. With prebiotic molecules raining down, the clock starts ticking earlier, giving evolution a head start. Of course, not everyone's convinced. critics point out that space is brutal. Intense radiation, extreme temperatures, and the fiery plunge through Earth's atmosphere could shred delicate molecules. Yet studies show some amino acids can survive these conditions, especially if shielded inside rocks. And here's the kicker. We've spotted complex molecules like ethanolamine, a key component of cell membranes, in interstellar gas clouds. The universe seems to be littered with life's spare parts. So does Panspermia solve the mystery or complicate it? On one hand, it expands the stage, suggesting life's ingredients could be universal. On the other, it just pushes the question further back. Where did space get its molecules? Either way, this theory forces us to look beyond our planet, because the answer to life's origins might be written in the stars. What if the key to life's origins wasn't hidden in the depths of the ocean or the void of space, but scattered along the shores of an ancient, radioactive beach? This is the intriguing premise of the radioactive beach hypothesis, a lesser-known but fascinating twist in the search for the universe's first complex molecules. Imagine Earth's earliest coastlines not as serene stretches of sand, but as shimmering, uranium-rich landscapes where the very ground beneath your feet crackled with energy. Here, radioactive elements like uranium and thorium, embedded in mineral sands, could have acted as natural catalysts, their steady decay providing the spark needed to drive molecular reactions. The science behind this idea is as elegant as it is surprising. When radioactive elements decay, they release energy in the form of alpha particles, beta rays, and gamma radiation enough to break apart simple molecules and rearrange them into more complex structures. Picture a grain of zircon, a mineral often found in beach sands, trapping uranium atoms inside its crystal lattice. Over time, as those atoms decay, they bombard nearby water and gases with energy, potentially forging amino acids or even nucleotides, the building blocks of DNA. Unlike lightning strikes or hydrothermal vents, which deliver intense but sporadic bursts of energy, radioactive decay offers a slow, steady simmer, perfect for nurturing delicate chemistry. But why beaches? It's all about the perfect storm of conditions. Shorelines provide a dynamic mix of water, air, and minerals, with tides constantly churning the sands and exposing new surfaces to reactions. Radioactive elements washed down from ancient rock formations would have concentrated in these coastal zones, creating natural hotspots for chemistry. Some researchers even speculate that the first self-replicating molecules might have emerged here, sheltered in tiny pores between sand grains, protected from the harshness of the open ocean or the sterilizing heat of vents. Yet for all its appeal, this theory remains on the fringes, and for good reason. The biggest hurdle, evidence. While lab experiments show radioactive minerals can produce organic molecules under controlled conditions, no one's yet found a smoking gun in the geologic record. Earth's oldest rocks have been recycled by plate tectonics, erasing much of our planet's earliest history. Plus, radioactivity is a double-edged sword. While it can create complex molecules, it can also shred them apart with ionizing radiation. Striking the right balance between construction and destruction would have been crucial, and we're still not sure how often nature nailed that equilibrium. Still, the radioactive beach hypothesis opens a thrilling possibility that life's origins might be tied to the same forces that power nuclear reactors. It's a reminder that the universe doesn't need gentle conditions to create complexity. Sometimes, all it takes is a little atomic chaos and the right stretch of sand. And if this theory holds water, it could mean the search for life elsewhere should include not just oceans and ice moons, but the shimmering, energetic shores of distant worlds. Sometimes the most unassuming materials hold the keys to life's greatest mysteries, like the mud beneath your feet. Enter the clay mineral hypothesis, a theory that suggests the universe's first complex molecules didn't just float freely or collide randomly. Instead, they might have found order on the surfaces of something as ordinary as clay. Picture Earth's primordial landscapes where volcanic activity spewed fine particles of minerals like montmorillonite and kaolinite into shallow pools. These clays aren't just dirt, they're dynamic, layered structures with a knack for chemistry. Their surfaces are riddled with tiny nooks and electrical charges, perfect for attracting and arranging molecules like a microscopic assembly line. Here's where it gets fascinating. In lab experiments, researchers have watched clays perform what seems like molecular magic. When simple organic compounds like nucleotides, the building blocks of RNA, are mixed with clay suspensions, something remarkable happens. The clay's surface acts like a template, coaxing these molecules to link into chains, sometimes even forming strands resembling RNA. It's as if the clay provides a blueprint guiding chaos into order. This isn't just random bonding, it's a step toward the self-replicating molecules that could have sparked life. And the clays don't stop there. They can also stabilize these fragile chains, protecting them from breaking apart in water or UV radiation. What makes this theory so compelling is how it bridges the gap between chemistry and biology. Random chemical reactions might create the ingredients for life, but without organization, they're just a soup. Clays offer a missing link, a way to arrange those ingredients into something functional. Some scientists compare it to a potter's wheel, shaping raw material into a vessel. In this case, the vessel could have been the first genetic material, capable of storing information and passing it on. Yet, like all great theories, this one isn't without its skeptics. Critics point out that while clays excel at assembling small RNA-like molecules, it's still a leap to get from there to a fully self-replicating system. And not all clays are created equal. Their chemistry varies wildly depending on their environment. Plus, there's the question of timing. Did Earth's early landscapes have the right mix of clays and organics at the same time? But here's the twist. The clay mineral hypothesis doesn't have to stand alone. Imagine a scenario where hydrothermal vents produced simple molecules, comets delivered extras, and clays waiting in tidal pools assembled them into something greater. It's a reminder that life's origins might not hinge on a single eureka moment, but on a symphony of unlikely collaborations. And if clays really did play this role, it changes how we look for life beyond Earth. Mars, for instance, has vast deposits of similar minerals. Could its ancient mudflats hold the echoes of a story we're only beginning to tell? Volcanic eruptions aren't just about lava and ash, they're some of the most electrifying events in nature, literally. When a volcano erupts, it doesn't just spew molten rock, it creates its own weather systems, complete with thunderstorms raging inside the plume. These aren't your average lightning strikes. They're hotter, more frequent, and pack enough energy to rip molecules apart and stitch them back together in entirely new ways. This phenomenon, known as volcanic lightning, might have been another cosmic chef in the kitchen of life's origins, cooking up complex molecules right in the heart of chaos. Think about the ingredients. A volcanic plume is a swirling mix of water vapor, carbon dioxide, nitrogen, and traces of methane and ammonia, the same basic elements that Miller and Urey used in their iconic experiment. But here's the difference. Instead of a lab flask, the reactions happen in a supercharged natural reactor. The lightning bolts act like a cosmic blender, breaking simple bonds and forging new ones at temperatures reaching 30,000 degrees Celsius. In this frenzy, scientists have detected organic compounds like formaldehyde and hydrogen cyanide molecules that are critical stepping stones to amino acids and nucleic acids. It's as if the volcano isn't just destroying the landscape, it's also laying the groundwork for something new to emerge. The evidence for this theory isn't just theoretical. In 2020, researchers analyzing the aftermath of Iceland's Fagradalsfjall eruption found traces of complex organic molecules clinging to volcanic ash particles. These weren't contaminants, they were synthesized right there in the plume, a testament to the raw creative power of volcanic lightning. And it's not just Earth where this could happen. Mars, with its history of massive volcanic activity, might have hosted similar chemical factories billions of years ago. Even Venus, despite its hellish surface today, could have once had lightning-lit skies churning out prebiotic molecules before its atmosphere turned toxic. But skeptics raise an eyebrow. Volcanic eruptions are violent, unpredictable events, hardly the stable environment you'd expect for delicate chemistry. The molecules formed in these storms would need to survive scorching temperatures, acidic rain, and rapid dispersal into the atmosphere. Yet nature has a way of finding pockets of opportunity. Lightning strikes are fleeting, but the sheer number of them in an eruption, sometimes thousands per hour, creates countless chances for molecules to form and find shelter in cooler ash or condensing water droplets. What's thrilling about this theory is how it expands the map of possible origins. Life's building blocks might not have needed a quiet pond or a deep sea vent. They could have been born in the sky amidst the thunder and fury of a planet's birth pangs. And if that's true, then the search for life's origins isn't just about finding the right ingredient. It's about recognizing the countless ways the universe can mix them together. Deep in the frozen voids between stars, where temperatures plunge hundreds of degrees below zero, an unexpected alchemy was taking place. Tiny grains of dust, no larger than a speck of smoke, became cosmic chemistry sets, each one a microscopic stage for the universe's first complex molecules. These interstellar ice grains, coated in layers of frozen water, carbon monoxide, and methane, might seem inert, but when bathed in the harsh glow of starlight or zapped by cosmic rays, they transformed into something extraordinary. Picture a snowflake laced with the raw ingredients of life, bombarded by ultraviolet radiation. The energy from these photons didn't just break molecules apart, it rearranged them, forging new bonds and creating compounds like formaldehyde, methanol, and even glycine, the simplest amino acid. What makes this process so remarkable is the cold. You'd think complex chemistry needs heat, but the icy grains prove the opposite. At near absolute zero, reactions that would normally fizzle out in warmer environments become stable, even encouraged. The ice acts like a trap, holding fragile molecules in place long enough for them to combine. And because space is so vast, these grains had millions of years to tinker with different arrangements, slowly building complexity in a slow-motion dance of atoms. The implications are staggering. If simple ice grains in the void can churn out life's building blocks, then the universe might be carpeted with them. Telescopes have already spotted complex organic molecules floating in nebulae, clinging to comets, and embedded in meteorites. Some scientists estimate that the Milky Way alone could contain billions of tons of these prebiotic compounds scattered like cosmic breadcrumbs. But the real twist, these icy laboratories might still be at work today. When comets or asteroids crash into planets including a young Earth, they could have delivered not just water but a starter kit of organic molecules. It's a humbling thought. The same chemical processes that happened in deep space billions of years ago might have seeded the raw materials for life right here. And if that's true, then the search for life beyond Earth isn't just about finding planets with water. It's about recognizing that the universe has been quietly mixing life's recipe since the beginning. Deep beneath the ocean's surface, where scalding water meets crushing pressure, lies a clue that might rewrite the story of life's origins: rust. Not just any rust, but iron-sulfur minerals like pyrite, better known as fool's gold. These unassuming compounds could have been the universe's first enzymes, kickstarting the chemical reactions that eventually led to life. This is the iron-sulfur world hypothesis, and it's not just a wild guess, it's rooted in the very chemistry that keeps you alive today. Take a breath. Right now, inside your cells, tiny iron-sulfur clusters are working like microscopic power plants, helping convert food into energy. These same structures, found in proteins across all living things, might have their origins in the porous rocks of ancient hydrothermal vents. Picture a vent chimney rich in iron and sulfur, its honeycomb surface buzzing with chemical activity. The minerals here don't just sit idle, they act as catalysts, grabbing molecules like carbon dioxide and hydrogen, shuffling their atoms and spitting out new compounds. Some scientists believe these vent minerals were the original proto-enzymes, performing the same basic tasks that modern proteins do, but without the complexity of biology. What makes this theory so compelling is how neatly it bridges geology and biology. Iron-sulfur clusters are simple, sturdy, and incredibly versatile. They can transfer electrons essential for energy reactions, and even form tiny conductive wires, almost like a primitive electrical grid. In lab experiments, researchers have recreated vent conditions and watched as these minerals assembled organic molecules step by step from simple gases. It's as if the vents were nature's first factories, with iron and sulfur as the assembly line workers. But the real kicker, this process solves one of life's biggest chicken and egg problems. Living systems need energy to build complex molecules, but they need complex molecules to harvest energy. Iron-sulfur clusters cut through the paradox. They don't require intricate machinery to function, just the right chemistry and a steady flow of hot, mineral-rich water. Over time, these reactions could have grown more sophisticated, eventually giving rise to the first self-replicating molecules. Of course, no theory is perfect. Critics point out that while iron-sulfur chemistry is powerful, it's not enough on its own to explain the leap from geology to biology. How did these mineral-based reactions transition into something alive? And why haven't we found conclusive evidence in ancient rocks? Still, the iron-sulfur world remains a favorite among scientists because it's grounded in the chemistry we see everywhere, from the vents at the bottom of the ocean to the enzymes in our cells. It's a reminder that life's spark might not have been some exotic event, but the quiet, relentless work of atoms doing what they've always done, finding new ways to combine. High-energy particles screaming across the cosmos at nearly the speed of light might seem like destroyers, not builders. But what if these violent cosmic rays were actually midwives for the universe's first complex molecules? This is the startling premise of cosmic ray catalysis, a theory that flips our intuition on its head. Imagine a drifting cloud of simple hydrogen and carbon monoxide in deep space. By all rights, it should stay frozen and inert. Yet when a cosmic ray, a proton accelerated by a supernova or black hole, slams into that cloud, something extraordinary happens. The collision doesn't just scatter atoms like billiard balls. It creates a cascade of secondary particles and radiation, ionizing molecules and sparking chemical reactions that wouldn't occur otherwise. Lab experiments here on Earth have proven this isn't just speculation. When scientists recreate space conditions in vacuum chambers, ultra-cold temperatures, simple gases, and bombard them with proton beams mimicking cosmic rays, the results are undeniable. Organic compounds like ethanol and acetic acid begin forming despite the apparent hostility of the environment. The secret lies in the energy transfer. Cosmic rays don't gently nudge molecules together, they blast them apart, creating highly reactive fragments called radicals. These unstable pieces then scramble to rebond, often in more complex arrangements than before. It's molecular chaos with surprisingly creative outcomes. This process could solve a long-standing space mystery: how we keep finding intricate organic molecules in places that should be chemical dead zones. Take the Taurus molecular cloud, a star-forming region where telescopes have detected over 50 different complex compounds, including sugars and alcohols. There's no starlight yet to drive reactions, no heat sources, just the constant rain of cosmic particles stirring the pot. The same physics might explain why amino acids appear on asteroids, or why Saturn's moon Titan has an atmosphere rich in organic haze. But here's where it gets truly mind-bending. Some calculations suggest cosmic rays could have even influenced life's handedness. the puzzling preference for left-handed amino acids in terrestrial life. When polarized cosmic rays whose spin aligns in one direction interact with molecules, they can impart a slight bias to certain molecular orientations. Over eons, that tiny asymmetry might have snowballed into the uniform chirality we see in biology today. Of course, like all theories, this one has its skeptics. While cosmic rays excel at starting reactions, they're less efficient at building really large molecules like proteins, and the dose matters too much radiation can break down complex organics faster than they form. Yet when combined with other environments like icy grains or hydrothermal vents, cosmic ray catalysis paints a picture of a universe where life's ingredients emerge in the unlikeliest places. The lesson: in the cosmic kitchen, sometimes you need a bolt of chaos to cook up something extraordinary. Forget everything you thought you knew about the origins of life, because the real game changer might have been hiding in plain sight: fat. Not the kind in your favorite snack, but microscopic droplets of lipids, the same molecules that make up cell membranes today. The lipid world hypothesis turns conventional wisdom on its head by suggesting these unassuming molecules weren't just latecomers to life's party. They might have been the first to arrive, setting the stage for everything else. Picture this: 4 billion years ago, Earth's shallow pools weren't just swirling with amino acids or RNA fragments. They were dotted with tiny lipid bubbles, forming spontaneously whenever fatty molecules met water. Unlike other complex molecules, lipids have a quirky talent: they self-assemble. Give them the right conditions, and they'll arrange themselves into hollow spheres, their water-loving heads pointing outward, their oily tails tucked inside. These aren't just random blobs, they're primitive cell membranes, complete with a barrier that can trap and concentrate other molecules. Lab experiments reveal how powerful this process could have been. When researchers mix simple fatty acids compounds likely present on early Earth with water and mild agitation, something remarkable happens. The lipids organize into stable vesicles, some even growing, dividing, and merging like microscopic protocells. No enzymes, no DNA, just physics doing the heavy lifting. And here's the kicker: these lipid bubbles can perform tricks that other prebiotic molecules struggle with. They create microenvironments, shielding delicate reactions from harsh external conditions. They concentrate nutrients inside their walls, turning a dilute soup into a potent biochemical lab. Some vesicles even develop gradients, mimicking the energy-harvesting systems of modern cells. What makes this theory so provocative is timing. If lipids formed early, they could have provided a scaffold for other molecules to organize long before RNA or proteins took center stage. Imagine a lipid bubble trapping a few strands of RNA inside. Suddenly, you've got a protected space where replication might occur, free from the chaos of the open environment. It's a biological snow globe, with lipids playing the role of both container and curator. But the lipid world hypothesis isn't without its skeptics. Critics argue that while lipids excel at self-assembly, they lack the informational punch of molecules like RNA, which can store and transmit genetic data. Plus, without proteins or enzymes, can lipid vesicles really evolve into something alive? Supporters counter that evolution isn't an all-or-nothing game. Maybe lipids laid the groundwork, creating the physical structures that later hosted life's chemical innovations. One thing's certain: this theory forces us to rethink the narrative. Life didn't necessarily begin with a single eureka molecule. Instead, it might have emerged from a collaboration, a lipid bubble whispering to a strand of RNA, "Let's build something together." And if that's true, then the search for life's origins isn't just about chemistry, it's about architecture. Because sometimes, before you can write the code of life, you need to build the house it lives in. Sunlight isn't just warmth and energy, it's a chemical architect. Billions of years ago, when Earth's atmosphere was a thick stew of methane, ammonia, and water vapor, ultraviolet radiation from our young sun didn't just illuminate the planet, it transformed it. High in the skies, UV photons slammed into simple molecules, tearing them apart and rearranging the pieces into more complex structures. This is photochemical synthesis, and it might explain how the building blocks of life first took shape not in oceans or vents, but in the air itself. Picture Earth's early atmosphere as a vast, chaotic laboratory. Unlike today's oxygen-rich skies, this was a reducing environment filled with gases that readily donate electrons, perfect for organic chemistry. When UV light hit methane, it could strip away hydrogen atoms, leaving behind reactive methyl radicals. These fragments then collided with nitrogen or carbon monoxide, forging compounds like hydrogen cyanide or formaldehyde. Step by step, sunlight assembled these intermediates into amino acids and even nucleobases, the letters of the genetic code. The process wasn't gentle. It was a molecular demolition derby, with bonds breaking and forming at a frenetic pace, but from that chaos emerged order. The proof isn't just theoretical. In 2015, researchers recreated these conditions in a lab, filling a chamber with early Earth gases and bombarding them with UV lamps. Within days, the mix contained not only amino acids but also the precursors to RNA. What's striking is how efficient this process could have been. Unlike lightning strikes or hydrothermal vents, which are localized events, sunlight blankets the entire planet, turning the upper atmosphere into a global factory for prebiotic molecules. This theory gains extra weight when we look at Titan, Saturn's haze-shrouded moon. Its nitrogen-methane atmosphere, bombarded by solar UV, produces a thick organic haze rich in complex molecules like benzene and cyanide. The Cassini spacecraft even detected vinyl cyanide in Titan's lakes, a compound that could form stable membranes in liquid methane, hinting at an alternate path for complexity. If Titan's skies can brew such chemistry without liquid water or geothermal energy, why not early Earth? But photochemical synthesis isn't a solo act. The molecules formed in the atmosphere would have rained down into oceans or lakes, where they could concentrate and interact further. Some models suggest this delivery system might have been crucial, supplying tidal pools or volcanic aquifers with a steady influx of organics. The atmosphere became a conveyor belt, lifting simple gases and lowering complex ones. Yet challenges remain. UV light doesn't just create, it destroys. Without a protective ozone layer, intense radiation could have broken apart complex molecules as fast as they formed. The solution might lie in cycles, molecules forming by day in the upper atmosphere, then sinking at night to cooler, shielded layers where they could accumulate. Or perhaps dust particles acted as umbrellas, shading fragile compounds long enough to matter. What's undeniable is the elegance of the idea. Life's precursors didn't need exotic environments or rare events. They might have been crafted in plain sight, under the same sun that still feeds every ecosystem today. And if that's true, then planets orbiting other stars, bathed in their own versions of sunlight, could be silently building the same molecular legacies, one photon at a time. Asteroid impacts aren't just forces of destruction, they're cosmic alchemists. When a space rock slams into a planet at speeds reaching 70,000 kilometers per hour, it doesn't just leave a crater. It creates a fleeting, superheated laboratory where the universe's first complex molecules could have forged. Picture an ancient Earth still cooling from its violent birth as a city-sized meteorite screams through the atmosphere. The instant it strikes, temperatures spike to thousands of degrees hotter than the surface of the sun, while pressures exceed 1,000,000 times Earth's atmosphere. In this hellish instant, something remarkable happens. Simple gases like carbon dioxide and nitrogen, compressed and superheated, undergo rapid chemical transformations, emerging as amino acids, sugars, and even nucleobases. This isn't speculation, it's been recreated in labs. Scientists use high-powered guns or laser pulses to simulate impact conditions, firing projectiles at gas mixtures resembling early Earth's atmosphere. The results are astonishing. Within microseconds, these experiments produce a cocktail of organic compounds, including adenine and guanine, 2 of the 4 bases in DNA. Real-world evidence backs this up too. The famous Murchison meteorite, which fell in Australia, contained over 90 amino acids, many of which show signatures of extreme heat and pressure. Even more telling, impact craters like Sudbury in Canada reveal mineral deposits consistent with sudden, high-temperature synthesis, proving asteroids don't just deliver molecules, they manufacture them on impact. Yet there's a paradox here. These same cataclysmic events that might have jump-started life also nearly sterilized the planet during the late heavy bombardment, a period 4 billion years ago when Earth was pummeled by asteroids. How could fragile organic molecules survive such violence? The answer lies in timing and location. Not all impacts are equal. Smaller asteroids, while still destructive, generate shorter, more localized heat pulses. Lakes or shallow oceans near impact sites could have acted as buffers, absorbing heat while providing a watery haven for newly formed molecules to cool and stabilize. Some models suggest these environments might even create a Goldilocks zone, far enough from ground zero to avoid utter devastation, but close enough to harvest the chemical fallout. This theory forces us to reconsider life's origins through a lens of chaos. Rather than gradual assembly in tranquil pools, complex molecules might have been forged in the blink of an eye, their blueprints hammered out in the fury of collisions. And if that's true, then life isn't just a product of Earth's chemistry, it's a testament to the universe's uncanny ability to create even as it destroys. The same fire that wiped out the dinosaurs might have kindled life's first sparks. Among all the molecules vying to be life's original architect, RNA stands out as the ultimate multitasker. Unlike DNA, which excels at storing information but needs proteins to do anything with it, RNA can both carry genetic instructions and catalyze chemical reactions. This dual talent makes it the perfect candidate for kickstarting life, if only we could figure out how it emerged from primordial chaos. The RNA world hypothesis has long dominated origins of life research, but recent breakthroughs are forcing us to rethink not just how RNA functioned, but how its basic building blocks could have formed at all. For decades, the biggest roadblock has been ribonucleotides, RNA's molecular Legos. These aren't simple molecules. Each one consists of a sugar ribose, a phosphate group, and a nitrogenous base. Getting these 3 pieces to link up under plausible early Earth conditions seemed impossible. Ribose, in particular, is notoriously fragile, breaking down almost as fast as it forms. But in 2016, a team at the MRC Laboratory of Molecular Biology cracked part of the puzzle. They discovered that when simple precursors like cyanamide and glycolaldehyde react in wet-dry cycles, think evaporating tidal pools, they can produce not just ribose, but all 4 nucleobases adenine, uracil, guanine, and cytosine in the same environment. Suddenly, RNA's ingredients weren't separate headaches, they were pieces of the same chemical cascade. Even more astonishing, phosphate, long assumed to be scarce in Earth's early oceans, might have been more accessible than we thought. New research suggests meteorites could have delivered reactive phosphorus minerals, while volcanic vents may have concentrated them in shallow hydrothermal pools. When combined with the right metals, these phosphates could have attached themselves to ribose and bases, completing the nucleotide trifecta. Lab experiments now show that under the right conditions, mild heating, gentle acidity, these components self-assemble into RNA like chains without enzymes. It's as if the universe had a recipe for RNA written into its chemistry all along. Yet the RNA world isn't without its gaps. While we've made strides in synthesizing nucleotides, getting them to form long, stable strands remains tricky. Prebiotic reactions tend to produce messy mixtures, not the clean, uniform chains biology relies on. And even if RNA formed, how did it start replicating? Modern cells use sophisticated protein machines to copy RNA, But in a world without proteins, RNA would have had to self-replicate, a feat no one has convincingly reproduced in labs. Some researchers argue this means RNA couldn't have been life's first molecule. Instead, they propose simpler molecular cousins like peptide nucleic acids pine or threose nucleic acids tine, which might have paved the way for RNA's takeover. What keeps the RNA world hypothesis alive despite these challenges is its sheer explanatory power. No other molecule bridges chemistry and biology so elegantly. Recent studies even show RNA can perform tasks we once thought required proteins, like building lipid membranes or regulating metabolic reactions. It's a Swiss Army knife in a primordial toolkit, capable of both storing information and getting work done. Maybe the answer isn't abandoning the RNA world, but expanding it, imagining a time when crude, imperfect RNA collaborated with minerals, lipids, or other molecules until biology stumbled upon the right formula. After all, life didn't have to start with a perfect system, just one good enough to survive long enough to improve. And if that's true, then RNA's greatest trick wasn't just being versatile. It was being patient. While hydrothermal vents get most of the attention for extreme chemistry, there's another hidden world where molecules might have cooked up deep beneath Earth's crust, where crushing pressures and scorching temperatures turn rock into a molecular forge. This is the deep Earth pressure cooker theory, and it suggests life's building blocks didn't just form on the surface or in the oceans, but kilometers underground, where the planet's own heat and pressure acted as a relentless chemical chef. Picture descending into a gold mine today where tunnels plunge over 3 kilometers below ground. At those depths, temperatures exceed 60 degrees Celsius and pressures mount to over 1,000 times sea level, conditions that seem inhospitable. Yet in these suffocating darkness, scientists have made startling discoveries. Water trapped in tiny fractures, isolated from the surface for billions of years, contains dissolved hydrogen, methane, and even complex hydrocarbons like ethane and propane. These aren't contaminants from mining equipment, they're relics of ancient subsurface chemistry, proof that organic molecules can form without sunlight, oxygen, or even liquid water as we know it. The secret lies in a process called serpentinization. When water seeps into Earth's mantle and reacts with iron-rich rocks like olivine, the minerals transform, releasing hydrogen gas as a byproduct. This hydrogen becomes fuel for further reactions, reducing carbon dioxide into methane or binding with nitrogen to form ammonia. In lab experiments mimicking these conditions using diamond anvil cells to simulate subterranean pressures, researchers have watched simple molecules rearrange into amino acids and even the ring structures found in nucleobases. It's chemistry powered by geology, where the very squeezing and heating of the planet become creative forces. What's revolutionary about this idea is how it redefines the habitable zone. We often assume life needs a sunlit ocean or a balmy pond, but if complex molecules can arise in the crushing depths, then anywhere with liquid water and geothermal activity becomes a candidate, not just on Earth, but on icy moons like Europa or Enceladus, where oceans slosh beneath miles of ice. Even Mars, with its extinct volcanoes and subterranean aquifers, might have hosted deep Earth chemistry long after its surface dried up. Yet the theory isn't without skeptics. While deep Earth reactions excel at producing small organics, it's unclear how these molecules could accumulate into larger structures without being broken down by the same extreme conditions. And if life's precursors formed underground, how did they reach the surface to kickstart biology? Some propose that volcanic activity or asteroid impacts could have blasted them upward, while others suggest deep sea vents might have served as intermediaries bridging the subsurface and ocean worlds. The most tantalizing clue comes from South Africa's Mponeng gold mine, where scientists found a bacterium called Candidatus desulphuridis audaxviator, thriving 2.8 kilometers underground. No sunlight, no oxygen, just radioactive decay as its energy source. If life can persist there today, why couldn't similar environments have built its components billions of years ago? The deep Earth pressure cooker theory forces us to look beyond the obvious into the planet's hidden chambers where heat, pressure, and time might have cooked up the unlikeliest recipe of all. The rhythmic rise and fall of tides might do more than shape coastlines. They could have been the universe's first molecular assembly line. Picture an ancient shoreline where shallow pools form under the midday sun, then vanish as water retreats, only to refill hours later. This endless cycle of wet and dry isn't just a geological process, it's a chemical powerhouse. Each time a tide pool evaporates, it leaves behind a concentrated soup of molecules packed so tightly that they can't avoid colliding. When the water returns, it reshuffles the deck, bringing fresh ingredients into the mix. Over thousands of cycles, this natural rhythm could have turned simple compounds into the complex molecules life needed to take hold. Lab experiments prove this isn't just poetic speculation. In 2012, researchers at the University of Cambridge recreated these conditions, dissolving nucleotides, RNA's building blocks, in tiny wells that cycled between wet and dry phases. The results were astonishing. With each evaporation, the nucleotides concentrated, forming sticky films that encouraged bonding. When rehydrated, these films didn't just dissolve back into chaos, they stabilized, allowing longer chains to persist. After just 30 cycles, the team observed strands of RNA like polymers reaching lengths that would take weeks to form in a static solution. It's as if the tides were acting as a molecular metronome, keeping time for life's first symphony. What makes tidal cycling so uniquely powerful is how it solves multiple problems at once. Concentration is one thing. Without it, molecules might drift apart before they ever interact. But cycling also provides energy. As water evaporates, it doesn't just leave molecules behind. It forces them into closer contact, overcoming the mild repulsion between negatively charged phosphates in nucleotides. The drying phase even helps remove water molecules that would otherwise hinder bond formation, a critical step for polymerization. And when the tide rushes back in, it doesn't just dilute everything, it selects for the sturdiest bonds, washing away weaker connections while preserving the ones that matter. This process isn't limited to RNA. The same principles apply to peptides, lipids, and even the precursors of metabolic cycles. In fact, tidal pools might have been the universe's first sorting algorithm, filtering random chemistry into something functional. Take a simple amino acid like glycine. Left alone in the ocean, it might float indefinitely, but in a cycling pool, it could link with others, forming short chains that fold into structures capable of rudimentary catalysis. Over time, these molecular echoes of the tides could have grown sophisticated enough to replicate, marking the transition from chemistry to biology. Yet tidal pools aren't a perfect solution. Critics point out that ultraviolet radiation on the early Earth would have been brutal, potentially breaking apart delicate polymers between wet phases. But nature is resourceful. Mineral coatings or organic films might have shielded molecules during the harsh daylight hours. And while cycling accelerates polymerization, it doesn't explain how specific sequences like those needed for genetic coding emerged from the noise. That might require other forces, such as mineral templates or electromagnetic fields, working in concert with the tides. The beauty of this theory lies in its universality. Tidal cycling isn't some rare planetary quirk. It's a fundamental feature of any world with liquid water and a moon. Mars once had vast oceans that would have experienced tides, and exoplanets orbiting red dwarfs could have tidal pools locked in eternal twilight. If wet-dry cycles really are a recipe for complexity, then the universe might be teeming with molecular experiments, each one rising and falling with the rhythm of its own cosmic shores. The tides that shaped our past could still be shaping possibilities we've yet to imagine. Sugar, it's not just the sweet stuff in your morning coffee. 4 billion years ago, these simple molecules might have been the universe's first stepping stones to life. Enter the foremost reaction, a bizarre, chaotic dance of chemistry that transforms formaldehyde, a one-carbon molecule, into a mixed bag of sugars, including ribose, the backbone of RNA. At first glance, it sounds like molecular alchemy. Pour in some formaldehyde, add a pinch of calcium hydroxide, and voila, sugars appear. But this process isn't as clean as a lab recipe. It's more like a bubbling, unpredictable cauldron where dozens of sugars form at once, with ribose as just one of many products. Here's how it works. Formaldehyde molecules link up in a series of reactions, growing longer chains that eventually fold into rings, the basic structure of sugars. The reaction doesn't need fancy enzymes or precise conditions. In fact, it happens spontaneously under mild heat and alkaline water, both of which were plentiful on early Earth. Meteorites like Murchison, packed with formaldehyde, suggest the raw ingredients were raining down from space, and ribose isn't the only useful output. The foremost reaction also produces glyceraldehyde and glycolaldehyde sugars that can link up to form even more complex molecules, but there's a catch. The reaction is notoriously messy. For every molecule of ribose it creates, dozens of other sugars clutter the mix, many of them useless or even destructive to proto-life. Imagine trying to build a house where the lumberyard delivers equal parts wood, sawdust, and termites. Without some way to filter out the good from the bad, ribose would drown in the chemical noise. That's where geology might have lent a hand. Certain minerals, like borates, have a knack for stabilizing ribose, shielding it from degradation while ignoring its molecular cousins. Other studies show that ribose can concentrate in evaporating tidal pools, leaving the junk sugars behind as water vanishes. What makes the foremost reaction so compelling isn't just its ability to make sugars, it's how neatly it slots into broader origin theories. For RNA world enthusiasts, it offers a plausible path to ribose without requiring miracles. Hydrothermal vent systems could have hosted the reaction in their mineral-rich chambers, while cosmic impacts might have jump-started it with sudden bursts of heat. Even the messiness fits. Life didn't need a perfect supply of ribose, just enough to get started, with natural selection handling the rest, yet the debate isn't settled. Some scientists argue that ribose is too fragile to have survived long in prebiotic soups, favoring alternative backbones like threose or peptide nucleic acids. Others point out that while the foremost reaction makes ribose, it doesn't explain how that ribose linked up with phosphates and nucleobases to form complete nucleotides. But here's the twist. Recent experiments show that under the right conditions, ribose can team up with cyanamide, a simple prebiotic chemical, to build nucleotide precursors in one pot. The foremost reaction might not be the clean, elegant solution we imagine when we picture life's origins, but that's the point. The universe isn't a meticulous chemist, it's a tinkerer, throwing spaghetti at the wall to see what sticks. And sometimes, amid all that chaos, something extraordinary emerges. In this case, a sprinkle of sugar that just might have sweetened the deal for life itself. Quantum mechanics isn't just the realm of particle physics. It might have been the silent architect of life's first molecules. At the atomic scale, particles don't behave like billiard balls. They flicker in and out of existence, vanishing through barriers as if by magic. This phenomenon, called quantum tunneling, lets particles cheat energy constraints, and some scientists believe it gave early chemistry a shortcut to complexity. Picture a hydrogen atom too weak to break a chemical bond under normal circumstances. Classical physics says it's stuck, but in the quantum realm, there's always a chance it teleports straight through the barrier, like a ghost walking through walls. In the chaotic soup of early Earth, where every reaction counted, this subtle trick could have tipped the scales toward life. The evidence isn't just theoretical. Modern enzymes, biology's catalysts, rely on tunneling to speed up reactions by factors of trillions. Take lactate dehydrogenase, an enzyme that helps convert sugar into energy. Studies show its hydrogen transfer reactions happen 1,000 times faster than classical chemistry predicts, all thanks to particles tunneling through energy hills instead of climbing them. If sophisticated proteins use this trick today, why couldn't simpler molecules have harnessed it 4 billion years ago? The implications are staggering. Reactions that should have taken millennia might have unfolded in days, knitting together amino acids or nucleic acids at life-friendly speeds. But here's where it gets eerie. Quantum effects are notoriously fragile, collapsing at the slightest disturbance, heat, noise, even a stray photon. How could delicate tunneling survive the molecular mayhem of a primordial soup? The answer might lie in extreme environments. Ice-filled cracks in glaciers or the nanopores of deep-sea vents could have provided just enough isolation, shielding quantum coherences long enough for them to matter. Some experiments even suggest that mineral surfaces, like those in clay, might have acted as quantum chaperones, organizing molecules while preserving their wave-like properties. The real twist: quantum biology might rewrite the timeline of life's origins. If tunneling helped reactions bypass energy barriers, then complex molecules could have formed in places we'd never expect: cold interstellar clouds, the shadowed craters of asteroids, even the frozen crusts of distant moons. Suddenly, the universe's recipe for life isn't limited by heat or pressure. It's governed by probabilities, where atoms defy classical rules and bonds form in the quiet flicker of quantum chance. Critics argue this is a stretch, that tunneling, while real, is too fleeting to have played a starring role. But consider this: in a prebiotic world where even tiny advantages compounded over eons, quantum effects didn't need to be dominant. Just frequent enough to nudge chemistry toward complexity. And if that's true, then life's blueprint wasn't just written in atoms. It was scribbled in the subatomic whispers of a universe playing dice with itself. Earth's magnetic field is more than just a shield against solar radiation. It might have been the invisible hand that shaped life's first molecules. Picture the young planet, its molten core churning like a dynamo, generating a magnetic field far stronger than today's. This wasn't just a protective bubble, it was a directional force capable of influencing even the tiniest particles. Some scientists believe this field could have acted like a cosmic sorting machine, aligning molecules in a way that made complex chemistry not just possible but inevitable. Here's how it might have worked. Many organic molecules, especially those critical for life, come in mirror image forms called enantiomers, like left and right hands. This property, known as chirality, is one of biology's deepest mysteries. Every living thing on Earth uses left-handed amino acids and right-handed sugars, a uniformity that defies random chance. If you synthesized these molecules in a lab without any outside influence, you'd get an equal mix of both. Yet nature chose one. Why? The answer could lie in Earth's magnetic field, subtly nudging molecules into alignment. When polarized light waves oscillating in a single plane passes through a magnetic field, it can interact with chiral molecules, breaking one form slightly more often than the other. Experiments have shown that under strong magnetic conditions, certain amino acids can develop a slight bias, just a few percent, toward one enantiomer. Over millions of years, that tiny imbalance could have snowballed into life's overwhelming preference for left-handed amino acids. It's as if the planet itself had a hidden preference written into the fabric of its magnetic field. This theory gains traction when we look beyond Earth. Meteorites like the Murchison, packed with amino acids, occasionally show slight enantiomeric excesses, hinting that cosmic magnetic fields might have played a role even before these molecules reached our planet. And it's not just about amino acids. RNA and DNA's helices twist in specific directions, a feature that might trace back to these early magnetic influences. But skeptics raise valid questions. Earth's magnetic field fluctuates, reversing polarity every few 100,000 years. Wouldn't that cancel out any chiral bias? Some researchers argue that local conditions like mineral surfaces or tidal pools could have amplified and preserved the effect despite these reversals. Others point to magnetic minerals in hydrothermal vents, which might have concentrated and stabilized aligned molecules in microscopic niches. What's fascinating is that this isn't just a historical curiosity. Modern labs use magnetic fields to purify chiral drugs, proving the principle still works. And if Earth's magnetism really did steer life's handedness, then planets without strong magnetic fields might host life with opposite chirality or no preference at all. Imagine an alien biosphere where proteins twist the wrong way, rendering their biochemistry incompatible with ours. The implications for astrobiology are profound. The mystery of life's handedness remains unsolved, but Earth's magnetic field offers a compelling clue. It's a reminder that life didn't emerge in isolation. It was shaped by forces as vast as planetary dynamos and as subtle as the spin of an electron. And if that's true, then the same invisible lines that guide compass needles might also have guided life's first steps. Before DNA, before RNA, before even the first proteins, there might have been a molecule so simple yet so powerful. It kick-started life's energy economy, thioesters. These unassuming compounds, barely a footnote in modern biochemistry, could have been the universe's first battery, storing and transferring energy in a world without enzymes or cells. The thioester world hypothesis is the underdog of Origins research, overshadowed by flashier theories like the RNA world. But what if it's the missing link between chemistry and biology? Thioesters are basically sulfur cousins of esters molecules where a carbon atom binds to an oxygen and a sulfur group. Today, they're best known for their role in metabolism, especially in the citric acid cycle, where acetyl-CoA, a thioester superstar, shuttles energy between reactions. But their real magic lies in their chemistry. Thioesters are high-energy molecules, meaning they're unstable in water, always itching to react. That might sound like a flaw, but in a prebiotic world, it's a feature. This instability makes them perfect for driving reactions forward, acting as molecular spark plugs in an era before ATP existed. Here's where it gets radical. The late biochemist Christian de Duve, who won a Nobel Prize for discovering lysosomes, argued that thioesters could have predated RNA as life's first energy currency. Imagine shallow volcanic pools rich in sulfur and iron, where simple organic acids like acetic acid reacted with hydrogen sulfide. Under the right conditions, maybe a jolt of geothermal heat or a zap of lightning, these ingredients could form thioesters spontaneously. Once formed, their energy could have been harnessed to build more complex molecules, stitching together amino acids or even nucleotides in a proto-metabolic dance. The evidence isn't just speculative. Lab experiments show thioesters can catalyze peptide bond formation, the same bonds that hold proteins together. They can also donate sulfur groups to other molecules, mimicking modern enzyme cofactors like coenzyme A. And unlike ATP, which requires intricate machinery to synthesize, thioesters form easily under conditions that likely existed near hydrothermal vents or volcanic springs. It's a no-frills energy system, perfect for a no-frills world. Yet the thioester world faces skepticism. Critics point out that while thioesters excel at energy transfer, they lack RNA's ability to store information. Without a way to encode genetic instructions, how could thioester-driven systems evolve? Supporters counter that evolution doesn't need to start with perfection, just functionality. Maybe thioesters laid the metabolic groundwork, creating a stable energy flow that later allowed RNA or proteins to take over. It's like building the electrical grid before inventing the computer. What makes this theory so compelling is its grounding in modern biology. Thioesters aren't relics, they're still embedded in our cells, hinting at an ancient origin. Even the infamous RNA world might owe a debt to thioesters. Some researchers propose hybrid scenarios where thioesters powered early metabolism while RNA handled replication, a division of labor that could explain how life's two essential functions, energy and information, co-evolved. The thioester world isn't just a niche idea, it's a reminder that life's origins might not hinge on a single molecule, but on a collaboration of chemical innovations. While RNA steals the spotlight, thioesters could have been the unsung backstage crew, quietly powering the show until biology's headliners were ready to take the stage. And if that's true, then the search for life's beginnings isn't just about finding the right molecule, it's about tracing the sparks that made complexity possible. Cosmic dust might seem like the universe's afterthought, just microscopic debris floating between stars, but these tiny grains could be the unsung heroes of life's origin story. Imagine a speck of dust no wider than a human hair, its surface pockmarked with countless microscopic pores and crevices. Far from being inert, these labyrinthine structures act like a celestial sponge, trapping molecules in their minuscule tunnels and shelves. In the harsh vacuum of space, where radiation shreds fragile compounds and temperatures hover near absolute zero, these dust grains become sanctuaries, shielding delicate chemistry from destruction while providing the perfect stage for complex molecules to assemble. Laboratory experiments reveal just how powerful this process can be. Scientists recreate interstellar conditions in vacuum chambers, chilling silicate or carbon grains to temperatures colder than Pluto, then coating them with icy layers of water, methane, and ammonia. When zapped with ultraviolet light or bathed in cosmic ray analogs, something remarkable happens. The ices break apart, forming reactive fragments that migrate into the dust's pores. Sheltered from further radiation, these fragments collide and combine, sometimes forming amino acids or sugars. The dust isn't just a passive bystander. Its intricate geometry acts like a microscopic reactor, guiding molecules into configurations that would be impossible in open space. The real magic lies in the dust's dual role as both shield and catalyst. Porous structures can concentrate molecules, increasing the odds of rare interactions. Minerals like olivine or graphite embedded in the grains might add metallic surfaces that speed up reactions, much like industrial catalysts in modern chemistry. Even more fascinating, some dust grains carry slight electric charges, creating localized electric fields that could polarize molecules, aligning them just right for bonding. It's as if each grain were a tiny factory, equipped with its own power supply and assembly line. This isn't just lab speculation. Telescopes have spotted the fingerprints of complex organics, polycyclic aromatic hydrocarbons, alcohols, even ethers clinging to dust in nebulae like Orion. The Atacama Large Millimeter Array in Chile has detected glycolaldehyde, a sugar precursor, swirling around infant star systems, likely bound to dust particles. And when comets like 67P/Churyumov-Gerasimenko co-swing by Earth, they bring dust rich in organic material, preserved from the solar system's birth. These findings suggest dust grains aren't just bystanders in cosmic chemistry, they're active participants, possibly even midwives to life's precursors. Yet the story doesn't end in space. When these dust grains clump into asteroids or comets and crash land on planets, they could deliver their molecular cargo intact. Earth's early oceans might have been seasoned with organics forged in the void, each grain a time capsule from the interstellar medium. Some researchers go further, suggesting that dust's porous structures could have sheltered molecules during planetary entry, surviving the fiery plunge through atmospheres. If true, then the same grains that nurtured chemistry in space might have seeded it on worlds like ours. Critics argue that dust's role, while compelling, is still just one piece of the puzzle. How did molecules escape their mineral prisons to interact freely? Could dust really produce enough complexity to matter? But here's the counterpoint: space is vast and time was plentiful. Over billions of years, even rare events add up. and if dust grains were even marginally efficient at assembly and delivery, their cumulative impact could be staggering. The beauty of this theory is its universality. Every star we see is surrounded by dust, and every galaxy is filled with it. If these unassuming grains truly are cosmic labs, then the raw materials for life might be more widespread than we ever imagined, not just in planets or oceans, but in the silent, glittering darkness between them. The universe's first complex molecules may have been forged not in grand cataclysms, but in the quiet, patient work of specks too small to see. Geothermal fields aren't just isolated hotspots, they're sprawling, interconnected networks that could have served as the universe's first collaborative labs for complex chemistry. Picture a young Earth, its crust riddled with geysers, hot springs, and bubbling mud pots, all linked by underground aquifers and steam vents. Unlike a single hydrothermal vent or tidal pool, these fields would have created a patchwork of micro-environments, each with its own unique mix of temperature, pH, and mineral content. One spring might be boiling and acidic, perfect for forging sulfur-rich compounds, while a nearby pool could be cooler and alkaline, ideal for stabilizing delicate sugars or nucleic acids. This diversity isn't just interesting, it's revolutionary. Instead of relying on one perfect setting to host every step of molecular assembly, geothermal networks could have handed off chemicals like a relay race, with each environment optimizing a different stage of the process. Take a hypothetical molecule's journey. Deep underground superheated water dissolves metals and sulfides from rock, creating a rich broth of reactive ingredients. As this fluid surges toward the surface, it passes through cooler fractures where minerals like iron or nickel catalyze the formation of simple organics, say, acetic acid or formaldehyde. By the time the solution reaches a shallow pool, evaporation concentrates these molecules, while ultraviolet light or clays further rearrange them into amino acids or nucleobases. If one step fails in one location, another might succeed just meters away. It's a fail-safe system where chemistry's trial and error plays out across an entire landscape rather than a single test tube. This idea gains traction when you look at modern geothermal regions like Yellowstone or Iceland. Even today, their springs host extremophiles microbes tailored to specific niches, from scalding sulfuric cauldrons to silica-rich terraces. But more striking are the chemical gradients these fields create. Researchers have measured stark variations in hydrogen, carbon dioxide, and ammonia levels between adjacent springs, proving that interconnected doesn't mean uniform. For prebiotic chemistry, this variability could have been a goldmine. A molecule formed in a scorching vent might drift into a tepid pool, gaining stability to interact with new partners. Or a lipid bubble assembling in one zone could trap nucleotides carried in from another, creating a rudimentary protocell. Critics might argue that geothermal fields are too chaotic for sustained chemistry, with eruptions or mineral deposits constantly reshaping conditions. Yet chaos could be the secret. Imagine a volcanic tremor fracturing a new pathway between two springs, suddenly mixing previously isolated reactants. Or seasonal rains diluting a basin, shifting its pH and sparking a fresh round of reactions. These disruptions wouldn't just randomize outcomes, they'd accelerate exploration of chemical space, increasing the odds of stumbling upon a winning combination. The implications stretch beyond Earth. Mars's ancient Tharsis volcanic province or Jupiter's moon Io, with its 100+ active geysers, might have hosted similar networks. Even planets without plate tectonics could generate geothermal variety through tidal heating or localized magma chambers. If interconnected fields really did drive chemical evolution here, then the universe's recipe for life might favor worlds with geologic restlessness where heat, water, and change collaborate across a stage much wider than we ever imagined. Acetylene, a simple molecule made of 2 carbon atoms and 2 hydrogens, might seem like an unlikely candidate for life's origins. but under the right conditions, this humble gas can transform into something far more intricate: aromatic molecules, the ring-shaped structures that form the backbone of everything from DNA bases to neurotransmitters. The acetylene hypothesis suggests that this unassuming compound could have been a critical stepping stone in the universe's journey toward complexity, especially in environments vastly different from Earth's. Take Titan, Saturn's largest moon, where rivers of methane carve valleys into icy bedrock. Here, acetylene isn't just a trace gas, it's a major player in the atmosphere, raining onto the surface and pooling in frigid lakes. When exposed to ultraviolet light or cosmic rays, these acetylene molecules don't just sit idle. They link up, forming longer chains and eventually assembling into benzene rings, the simplest aromatic structure. This isn't speculation. NASA Cassini probe detected benzene and other polycyclic aromatics floating in Titan's hazy orange skies, proof that acetylene's transformative chemistry isn't just possible, it's happening right now, 800 million miles away. Lab experiments back this up. Researchers simulating Titan's conditions, freezing temperatures around -180 degrees Celsius, with a nitrogen-methane atmosphere, have watched acetylene molecules polymerize into complex aromatics with surprising ease. Some studies even suggest that under the moon's cryogenic conditions, these molecules could stack into sheets, resembling the structure of graphite or the precursors to organic dyes. It's a reminder that complexity doesn't always need warmth or liquid water. Sometimes all it takes is a dash of radiation and a molecule desperate to bond. But the real magic happens when these aromatics interact with other compounds. On Earth, benzene rings are the skeletons of life's most essential molecules. The adenine and guanine in your DNA, the tyrosine in your neurotransmitters, even the chlorophyll in plants. If acetylene could form such rings on a young Earth, perhaps in volcanic plumes or icy cometary grains, then the leap from chemistry to biology becomes a little less mysterious. The same processes might even explain why meteorites like Murchison are packed with aromatic hydrocarbons, hinting that this chemistry isn't confined to our solar system. Of course, skeptics point out that aromatics alone don't make life. Benzene is famously stable, sometimes too stable, resisting further reactions that could lead to functional biology. But nature is resourceful. Add a little ammonia or hydrogen cyanide to the mix, and those inert rings can sprout nitrogen or oxygen groups, transforming into the nucleobases that encode genetic information. It's like upgrading a simple Lego block into a hinge or a wheel, unlocking new possibilities for assembly. The acetylene hypothesis forces us to rethink the boundaries of habitability. If Titan's frozen wastelands can brew aromatic chemistry, then so could countless exoplanets with methane-rich atmospheres. And if acetylene was a universal architect, quietly constructing life's scaffolding across the cosmos, then the ingredients for complexity might be more common than we ever imagined. The universe, it seems, has a flair for turning simple gases into something extraordinary, one carbon bond at a time. In the chaotic molecular soup of early Earth, where countless compounds collided at random, one force might have imposed order from the disorder: electricity. Not the dramatic arcs of lightning, but the subtle, pervasive pull of electrostatic attraction. Picture the surface of a mineral like pyrite, commonly known as fool's gold. To the naked eye, it's just a shiny rock, but at the atomic scale, it's a landscape humming with activity. Pyrite's crystalline structure creates patches of positive and negative charge, turning its surface into a molecular dance floor where oppositely charged compounds line up like obedient partners. This is electrostatic surface catalysis, and it could explain how life's ingredients went from a disorganized jumble to a finely tuned assembly line. Laboratory experiments reveal the astonishing power of this process. When researchers expose simple organic molecules like amino acids or nucleotides to charged mineral surfaces, something remarkable unfolds. The minerals don't just passively host reactions, they actively orchestrate them. Pyrite, for instance, can coax formic acid, a simple one-carbon compound, into linking up with ammonia to form glycine, the smallest amino acid. Other minerals, like olivine or montmorillonite clay, have been shown to align RNA components into chains, acting as primitive templates that reduce the randomness of chemical synthesis. It's as if the rocks themselves were the first chemists, using their atomic architecture to direct the show. What makes electrostatic catalysis so compelling is its versatility. Unlike hydrothermal vents or tidal pools, which require specific environments, charged minerals are everywhere, in volcanic ash, riverbeds, even interstellar dust. And their influence isn't limited to bonding. These surfaces can also filter molecules, favoring the survival of certain structures over others. Case in point, certain clays have a knack for selecting left-handed amino acids over their right-handed counterparts, potentially explaining why all known life uses one chiral form. This isn't just chemistry, it's nature's version of quality control. The implications stretch far beyond Earth. Mars's rusty surface is rich in iron oxides, which share pyrite's talent for electrostatic organization. Europa's icy crust may harbor similar minerals beneath its frozen shell. Even exoplanets orbiting red dwarfs bathed in intense stellar winds could have surfaces crackling with electrostatic potential. If charged minerals really did guide life's molecular beginnings, then the universe might be dotted with invisible assembly lines, quietly arranging atoms into ever more complex patterns. Yet this theory isn't without its skeptics. Some argue that while electrostatic surfaces excel at assembling small molecules, they struggle to explain the leap to true polymers like proteins or RNA. Others point out that ancient mineral compositions may have differed from modern samples, leaving gaps in our experimental recreations. But here's the counterargument: evolution doesn't demand perfection, just progress. Maybe these surfaces didn't build finished products, but they didn't need to. Their role might have been to nudge chaos toward order, providing the slightest edge that made all the difference over eons. The beauty of electrostatic catalysis lies in its simplicity. No elaborate energy sources or rare conditions, just the universal tug of positive and negative, turning random chemistry into something purposeful. And if that's true, then life's origins might not hinge on extraordinary events, but on the ordinary magic of atoms finding their way home. Before ATP became biology's universal energy coin, there might have been a rougher, more rugged molecule handling the job: polyphosphate. These chains of linked phosphate groups found in every cell today are often overshadowed by their glamorous cousin ATP, but dig deeper and their chemistry tells a different story. Polyphosphates are workhorses, stable, versatile, and capable of storing energy in bonds that can be snapped apart on demand. What if they weren't just a backup system, but the original power source for life's earliest reactions? Modern cells still rely on polyphosphates for tasks ATP can't handle. Certain bacteria stockpile them as emergency energy reserves, like molecular batteries tucked away for lean times. Even human cells use polyphosphates to trigger blood clotting or regulate stress responses. But here's the clincher: polyphosphates don't need elaborate enzymes to form. Unlike ATP, which requires a dizzying assembly line of proteins to synthesize, polyphosphates can emerge from simple geology. Volcanic vents, for instance, spew phosphorus-rich minerals that, when heated and pressurized, polymerize into long phosphate chains. Imagine a young Earth, its crust riddled with geothermal activity, where steam and acidic fluids leached phosphates from rocks, then concentrated them into simmering pools. No biology required, just physics and chemistry doing the heavy lifting. Experiments back this up. When researchers simulate volcanic conditions, superheated water, minerals like apatite, and a dash of acidity, polyphosphates form spontaneously. They're not just stable, they're reactive, capable of phosphorylating other molecules, essentially donating phosphate groups to fuel reactions. This is huge because phosphorylation is life's signature move. It's how cells activate proteins, copy DNA, and store energy. If polyphosphates were abundant on early Earth, they could have handed phosphate groups to nascent organic molecules, jump-starting proto-metabolic cycles long before ATP existed. The plot thickens when you consider polyphosphates' other talents. These chains can bind metals like iron or calcium, creating clusters that mimic modern enzyme cofactors. Some scientists believe these metal polyphosphate complexes might have been the first catalysts, guiding reactions toward greater complexity. Even more intriguing, polyphosphates can stabilize RNA, preventing it from degrading in water, a crucial step if RNA world theories hold weight. It's as if polyphosphates were the multitasking foundation upon which later systems, like ATP, could evolve. Yet the polyphosphate puzzle isn't without missing pieces. Critics point out that while volcanic sources could produce these molecules, early Earth's oceans were rich in calcium, which binds phosphates into insoluble rocks. How did enough polyphosphates stay free to matter? One answer lies in acidic hydrothermal vents, where low pH keeps calcium at bay, allowing phosphates to dissolve and polymerize. Another possibility involves meteorites, which delivered reactive phosphorus minerals like schrebersite compounds that bypass Earth's calcium trap entirely. What's striking is how this theory reframes life's energy story. ATP is elegant, but it's also fragile, a high-maintenance molecule demanding constant replenishment. Polyphosphates, by contrast, are durable, forgiving, and geologically plausible. They suggest life didn't start with perfection, but with whatever worked, a rough and ready energy system that later refined itself into the sleek ATP machinery we know today. And if that's true, then the search for life's origins isn't just about carbon or water. It's about phosphorus and the unassuming chains that might have powered biology's first sparks. Comet impacts aren't just delivery trucks dropping off pre-made organic molecules, they're cosmic chemistry sets, violently transforming simple ingredients into complex compounds during their fiery descent. When a comet screams through Earth's early atmosphere at 60,000 kilometers per hour, the shockwaves alone generate pressures exceeding 100,000 atmospheres and temperatures rivaling the sun's surface. In this maelstrom, ordinary molecules like water, ammonia, and carbon dioxide don't just survive, they reinvent themselves. Laboratory shock tube experiments reveal the astonishing alchemy at work. Under these extreme conditions, these simple compounds shatter and recombine into amino acids, sugars, and even nucleobases in milliseconds. It's not panspermia, it's shock synthesis, where the very act of arrival cooks up life's ingredients on the spot. Take the infamous Murchison meteorite, long celebrated for its cargo of intact amino acids. Recent analyses show some of these molecules bear isotopic signatures of extreme heat, hinting they weren't just passengers, but products forged during atmospheric entry. This dual role changes everything. Instead of relying solely on interstellar clouds or asteroid surfaces to manufacture complexity, comets become mobile laboratories capable of both transporting and transforming molecules in transit. Imagine a snowball of frozen ammonia and methane, pristine from deep space. As it plummets, friction vaporizes its outer layers, creating a temporary chemical reactor in its wake. By the time debris reaches the ground, it's laced with compounds that didn't exist before the plunge. The numbers are staggering. Simulations suggest a single-kilometer-wide comet could deposit over 100,000 tons of organic material, half-formed during entry. Factor in the late heavy bombardment when Earth endured millions of impacts and the cumulative effect becomes profound. These aren't just random deliveries, they're targeted injections of freshly synthesized molecules, precisely where the energy of impact can drive further reactions in shallow waters or tidal pools. Yet skeptics raise a crucial point. Doesn't such violence destroy more than it creates? The answer lies in gradients. While the comet's leading edge faces apocalyptic heat, its trailing materials experience milder conditions, like ingredients tossed into a wok. Some sear instantly while others warm gently. Studies of Comet Wild 2's dust, returned by NASA's Stardust mission, show organic molecules surviving mostly intact, suggesting pockets of material can cheat destruction. Even more compelling are hypervelocity impact experiments at facilities like the University of Kent's light gas gun. When projectiles strike amino acid-laden ice at cosmic speeds, up to 20% of the compounds not only survive, but polymerize into longer chains, proving delivery and synthesis aren't mutually exclusive. This duality reshapes how we view life's cosmic connections. Europa's ice crust or Titan's methane lakes might lack certain prebiotic ingredients locally, but a well-timed comet could supply both raw materials and the energy to assemble them. The universe's recipe for complexity grows richer, no longer just slow-cooked in nebulae or hydrothermal vents, but flash-fried in the heat of celestial collisions. Each impact becomes more than a catastrophe, it's a catalyst, turning sterile ingredients into the first whispers of chemistry that might someday awaken. RNA might be biology's superstar, but what if it wasn't the first molecule to crack the code of life? Enter peptide nucleic acid DNA for short, a quirky hybrid that blends the simplicity of proteins with the information-carrying genius of DNA. Picture this: instead of RNA's delicate ribose phosphate backbone, DNA builds its structure from sturdy peptide bonds, the same links that hold proteins together. This isn't just a minor tweak, it's a game changer. Unlike RNA, which struggles to form long, stable chains without enzymes, DNA assembles easily in water, resists breakdown by heat or radiation, and even binds more tightly to DNA than DNA itself. It's as if nature had a rough draft before settling on RNA's final design. The real allure of DNA lies in how it sidesteps RNA's infamous paradox. RNA's brilliance, its ability to both store information and catalyze reactions, comes with a catch: making RNA requires RNA. Enzymes built from RNA are needed to synthesize RNA, creating a circular dilemma biologists call the chicken and egg problem. DNA offers an elegant escape. Its peptide backbone forms spontaneously under conditions found near hydrothermal vents or volcanic pools. No enzymes required. Once assembled, DNA can mimic RNA's most crucial trick: complementary base pairing. Lab experiments show DNA strands faithfully copy sequences, passing along information just like genetic material. It's a molecule with training wheels, simple enough to emerge from prebiotic chaos, but sophisticated enough to bootstrap the transition to RNA. Support for this idea comes from unexpected places. Deep sea vents rich in ammonia and formaldehyde, key DNA precursors, harbor mineral surfaces that could have templated early DNA synthesis. Meteorites like Murchison carry amino acids perfectly suited for building DNA's backbone, suggesting space might have seeded Earth with ready-made parts. Even more compelling, DNA's structure solves RNA's stability problem. While RNA strands unravel in acidic or salty conditions, DNA remains unfazed, a trait that would have been invaluable on a young Earth with wildly fluctuating environments. Skeptics counter that DNA's simplicity might be its limitation. Without RNA's versatile ribose ring, could DNA have catalyzed the diverse reactions needed for life? Recent research offers a clue. Certain DNA sequences fold into shapes that accelerate chemical reactions, though not as efficiently as modern ribozymes. But perfection isn't the goal, functionality is. A crude DNA replicator, even one that made mistakes, could have paved the way for RNA's later dominance. The DNA world hypothesis doesn't discard RNA's importance, it reframes its origin story. Instead of RNA emerging fully formed from primordial soup, DNA might have been the bridge between random chemistry and coded biology. Imagine a molecular relay race with DNA passing the baton to RNA once environments stabilized and enzymes evolved. This nuanced view doesn't just solve a puzzle, it expands life's possible blueprints. If DNA thrived here, maybe it's thriving still, hidden in the acidic clouds of Venus or the methane seas of Titan, proof that life's origins might be stranger and simpler than we ever dreamed. We assume water was life's original solvent, the universal medium where all the magic happened. But what if we've been overlooking a far more exotic candidate? Enter supercritical carbon dioxide, a state of matter so strange it defies conventional categories. When CO2 is heated and pressurized beyond its critical point, around 31 degrees Celsius and 74 atmospheres, it transforms into something neither fully gas nor liquid. This supercritical fluid flows like a gas, penetrates materials like a solvent, and dissolves substances water can't touch. And on early Earth, where volcanic activity churned out vast amounts of CO2 under extreme pressures, vast reservoirs of this enigmatic fluid might have existed, creating pockets of chemistry utterly alien to our water-centric expectations. The beauty of supercritical CO2 lies in its selectivity. Unlike water, which eagerly breaks apart fragile molecules through hydrolysis, this fluid is gentler on unstable compounds. Lab experiments show supercritical CO2 excels at preserving delicate organic molecules that would disintegrate in water. Think amino acids with reactive side chains or early nucleotide precursors. It's like comparing a sledgehammer to a pair of tweezers. Where water smashes, CO2 carefully manipulates. This property could have been crucial for assembling life's building blocks without immediately destroying them. But the surprises don't stop there. Supercritical CO2 has a unique talent for tuning its own properties. Adjust the temperature or pressure slightly, and its solubility changes dramatically. Imagine a primordial vent system where CO2 fluctuated between supercritical and near-critical states, creating dynamic zones where molecules dissolved, concentrated, and reacted in cycles. In such an environment, simple compounds like formic acid or hydrogen cyanide could have been coaxed into more complex structures, with the fluid itself acting as both reactor and regulator. Even more intriguing is CO2 relationship with lipids. Modern cells use fatty molecules to build membranes, but forming those membranes in water requires elaborate biochemistry. Supercritical CO2, however, spontaneously arranges lipids into stable, vesicle-like structures, no enzymes needed. Researchers at NASA Ames Research Center demonstrated this by creating lipid membranes in supercritical CO2 that closely resemble those in living cells. It's a tantalizing hint that the first protocells might not have formed in oceans at all, but in pressurized CO2 chambers beneath volcanic plains. Critics raise valid concerns. Could supercritical CO2 have existed in large enough quantities to matter? Geologic evidence suggests yes. Ancient subduction zones and hydrothermal systems likely hosted extensive CO2-rich fluids, especially during Earth's more volcanic past. And while this solvent might excel at protecting certain molecules, it struggles with others like salts or highly polar compounds essential to modern biology. But early life didn't need perfection, just a foothold. Perhaps supercritical CO2 was a niche player, bridging the gap between random chemistry and the RNA or lipid worlds before water took over. The implications ripple beyond Earth. Mars's Hellas Basin, with its history of volcanic activity and high-pressure CO2 deposits, might have harbored similar environments. Even Venus's scorching surface, where CO2 exists in a supercritical state today, forces us to reconsider the boundaries of habitability. If life's chemistry could start in such extreme solvents, then our search for extraterrestrial life needs to widen beyond water worlds to planets where carbon dioxide isn't just an atmospheric afterthought, but the hidden architect of complexity. Supercritical CO2 doesn't just challenge our assumptions, it rewrites the rules. In its elusive state between phases, it offers a glimpse of how life might have danced on the edge of impossibility, turning the universe's harshest conditions into a cradle for creation. And if that's true, then the story of life's origins isn't just about the chemistry we know, but the chemistry we've yet to imagine. Imagine a world where the spark of life didn't come from sunlight or lightning, but from a shimmering blue-white metal bubbling up from the depths. Zinc, often overlooked in the grand narrative of life's origins, might have been the universe's unsung architect, quietly catalyzing reactions that set the stage for biology's first act. This is the zinc world hypothesis, and it hinges on a simple but profound idea. Before proteins perfected their roles as enzymes, metal ions like zinc could have been nature's first catalysts, guiding simple molecules into complexity with effortless precision. Here's why zinc stands out. Unlike bulkier organic molecules, zinc ions are tiny, versatile, and pack a powerful electrostatic punch. In modern cells, zinc sits at the heart of over 300 enzymes, from DNA-building proteins to those that regulate metabolism. Its secret, a unique ability to stabilize charged intermediates in reactions, acting like a molecular glue that holds fleeting compounds together long enough for bonds to form. Picture a hydrothermal vent on the early Earth, where zinc-rich fluids spew from mineral chimneys. In this turbulent environment, zinc ions could have latched onto simple molecules like carbon dioxide or hydrogen sulfide, coaxing them into reactions that produced organic acids or even amino acids. No sophisticated enzymes required. The evidence isn't just theoretical. Lab experiments simulating these conditions, zinc salts dissolved in hot, alkaline water mimicking vent fluids, have produced startling results. When researchers add precursors like pyruvate or formaldehyde to the mix, zinc catalyzes their transformation into more complex molecules, sometimes at rates rivaling modern biological enzymes. Even more compelling, zinc's affinity for sulfur could have helped assemble iron-sulfur clusters, the ancient energy converters still found in every living cell today. It's as if zinc were a molecular matchmaker, introducing key players to one another in chemistry's earliest networking events. But zinc's talents don't stop at catalysis. This metal also excels at structure. RNA molecules, often touted as life's first genetic material, fold into functional shapes only with the help of ions like zinc. Without them, RNA strands flop around like untied shoelaces, useless for replication or catalysis. In zinc-rich environments, though, RNA could have gained the rigidity needed to perform its dual roles, bridging the gap between chemistry and biology. Critics might argue that zinc alone isn't enough to explain life's leap from simple to complex. After all, biology runs on teamwork, with countless elements playing supporting roles. Yet zinc's prevalence in ancient hydrothermal systems, confirmed by geologists studying rocks from Earth's earliest oceans, suggests it wasn't just a bit player. Some vent fields, like those in the Atlantic's lost city, still shimmer with zinc-bearing minerals today, hinting at the metal's enduring legacy. The zinc world hypothesis doesn't just rewrite life's origin story, it expands the map of where to look for life beyond Earth. Europa's subsurface ocean, enriched by hydrothermal activity, or Mars's ancient hot springs, now dry but once possibly zinc-rich, could have hosted similar chemistry. If a humble metal could midwife life here, why not elsewhere? Zinc's quiet genius lies in its simplicity, proving that sometimes the universe's most profound breakthroughs come not from grand designs but from elemental whispers. The atmosphere isn't just empty space, it's a bustling chemical laboratory where microscopic droplets could have concentrated life's ingredients against all odds. Picture Earth's early skies, thick with water vapor, methane, and ammonia, constantly churning with storms and volcanic plumes. Within this chaotic mix floated countless aerosol droplets, tiny liquid or solid particles suspended in air, each one a self-contained reactor no wider than a human hair. These droplets weren't passive bystanders. Their surfaces and interiors could have acted like molecular traps, gathering sparse reactants from the surrounding gas and cramming them into tight spaces where collisions and chemistry became inevitable. Modern studies of aerosol behavior reveal just how potent this process can be. In cloud chambers today, scientists observe droplets concentrating trace gases like formaldehyde or hydrogen cyanide by factors of thousands, creating localized hotspots where reactions that would take years in open air unfold in hours. What makes aerosols so effective isn't just their ability to gather molecules, it's their dynamic nature. Unlike stagnant ponds or vents, aerosols constantly cycle through evaporation and condensation, creating pulses of concentration and dilution. Imagine a droplet forming around a speck of volcanic dust, absorbing nitrogen oxides and hydrocarbons as it grows. When the droplet evaporates in drier air, those molecules don't just dissipate, they're left clinging to the particle's surface in a densely packed film, ripe for bonding. Then, when the droplet reforms during the next cycle, it carries these newly formed compounds into its core, shielding them from destructive ultraviolet radiation. It's a rhythmic, planet-scale purification system, sifting through atmospheric chaos to assemble order one droplet at a time. Laboratory experiments back this up. When researchers simulate prebiotic atmospheres in reaction chambers, filling them with water vapor, carbon dioxide, and traces of ammonia, then expose the mix to ultraviolet light or electrical discharges, something remarkable happens. The aerosols that form quickly accumulate amino acids and sugars, even in concentrations far too dilute to react in bulk gas. Some studies suggest that the thin, organic-rich films coating these droplets might even catalyze their own growth, acting as primitive metabolic systems that feed on atmospheric gases. The real intrigue lies in the aerosol's versatility. High-altitude ice crystals could have hosted reactions at freezing temperatures, favoring the stability of delicate ribose or nuclear bases. Meanwhile, acidic droplets near volcanic plumes might have driven the polymerization of amino acids into peptides. This division of labor isn't just convenient, it's revolutionary. Instead of relying on a single environment to handle every step of molecular assembly, the atmosphere could have partitioned chemistry across multiple microenvironments, each optimized for a different task. Critics argue that aerosols are too transient to sustain meaningful chemistry, with most droplets evaporating or falling as rain within days. But here's the counterpoint. Earth's early atmosphere was likely far hazier than today's, with aerosol lifetimes extended by constant replenishment from volcanoes and photochemical reactions. Even brief windows could have been enough. A single droplet might only last a week, but if it produces a handful of amino acids in that time, trillions of droplets working in parallel would generate staggering quantities over millennia, enough to seed oceans or lakes during rainfall. The implications stretch beyond our planet. Titan's orange haze, composed of complex organic aerosols, proves this chemistry isn't unique to Earth. Even Venus's sulfuric acid clouds, despite their hostility, might be forging organic molecules right now under different rules. If atmospheric droplets truly served as universal reaction vessels, then the skies of exoplanets, not just their oceans, could be teeming with chemical innovation. The universe's first complex molecules might not have simmered quietly in tidal pools or hydrothermal vents. They could have been born in the clouds, riding the winds of a young world until they were ready to fall and awaken. Deep in the swirling chaos of early Earth's chemistry, something remarkable happened. A reaction began copying itself, not just once but over and over, like a molecular echo growing louder with each repetition. This is the power of autocatalysis, where the products of a reaction fuel their own creation, forming a self-sustaining loop. Imagine a single molecule of acetic acid floating in a primordial pool. Under the right conditions, it could trigger a cascade of reactions that produce more acetic acid alongside other compounds, each cycle amplifying the process exponentially. No enzymes, no cells, just raw chemistry caught in a feedback loop of its own making. This isn't just a neat trick, it's the closest thing we've found to a chemical spark that could ignite life itself. The magic of autocatalytic sets lies in their ability to turn randomness into order. In the 1970s, mathematician Stuart Kauffman proposed that under certain conditions, random mixtures of molecules could spontaneously organize into networks where each reaction's output fuels another's input. Picture a room full of dominoes, not arranged in a line but in an intricate web where knocking over one sets off 3 others, which in turn trigger even more. Now replace those dominoes with molecules like amino acids or lipids, and you've got a system where complexity builds without external direction. Lab experiments have proven this isn't just theory. When researchers mix simple organic compounds with metal catalysts, they've observed loops where molecules like formic acid or peptides generate copies of themselves, sometimes even branching into new reactions that stabilize the entire network. But how does a chemical loop become lifelike? The key is interdependence. In a true autocatalytic set, no single reaction can sustain itself alone. Each depends on the others, creating a web of mutual support. Modern cells work the same way. Your metabolism isn't a single pathway but a tapestry of cycles feeding into one another. Early autocatalytic sets might have achieved a crude version of this, with molecules like ribonucleotides or fatty acids forming cooperative alliances. Some researchers even suggest that these sets could exhibit a primitive form of evolution, with slight variations in reaction speeds or byproducts leading to fitter networks that dominate their chemical environment. It's a haunting echo of Darwinian competition, playing out at the molecular level long before biology took the stage. Yet autocatalysis isn't a silver bullet. Critics point out that most laboratory examples require carefully tuned conditions, specific temperatures, pH levels, or metal ions that might have been rare in the wild. And while these sets can replicate, they lack the precision of genetic coding, making errors that could unravel the entire network. But here's the twist: imperfection might have been the catalyst for life's next leap. A sloppy autocatalytic set could stumble upon a molecule like RNA, which not only replicates but carries information, stabilizing the system while adding a layer of heredity. Suddenly, chemistry isn't just echoing, it's remembering, adapting, innovating. The beauty of this theory is how it reframes life's origins. Instead of searching for a single eureka molecule, we're left with a vision of escalating collaboration, molecules teaching each other to persist, to collaborate, to grow. Autocatalysis doesn't just explain how life might have started, it hints at why. In a universe that tends toward disorder, these loops are pockets of rebellion, where chaos curls back on itself and becomes something new. And if that's true, then the boundary between chemistry and biology isn't a line, but a spinning wheel, turning faster and faster until one day, against all odds, it catches fire. From bubbling hydrothermal vents to radioactive beaches, from cosmic dust to volcanic lightning, our journey through the universe's first complex molecules has revealed something extraordinary. There's no single path to life's origins, but rather a dazzling web of possibilities, each theory adding another thread to the tapestry. Some ideas fit together like puzzle pieces, tidal cycles concentrating molecules that claim minerals then organize, or cosmic rays sparking reactions that iron-sulfur clusters later refine. Others stand as bold alternatives, challenging us to rethink everything we assumed about life's requirements. What's striking isn't just the diversity of theories, it's how many of them might be true simultaneously. Perhaps RNA didn't emerge alone, but with thioesters powering its reactions and lipid bubbles protecting its folds. Maybe Earth's magnetic field gently steered molecules into chirality while deep Earth pressures forged their backbone. The beauty of science lies in this complexity. Every discovery, whether it's amino acids in meteorites or autocatalytic sets in labs, doesn't narrow the possibilities, it expands them. This isn't just chemistry, it's cosmic archaeology. Each hypothesis, no matter how wild or fringe, peels back another layer of our shared history. When we study how molecules assembled in the void or cooked in hydrothermal cauldrons, we're tracing the steps that led to you, me, and every living thing on Earth. That's why even the most outlandish ideas matter, because somewhere in the interplay of these theories, the universe's greatest magic trick unfolds. A handful of simple atoms, given enough time and the right conditions, began to dance. And that dance never stopped. So tell us which of these origin stories resonates with you. Do you see life beginning in the electric fury of a volcanic storm, or the patient rhythm of tidal pools? Maybe you're drawn to the quiet elegance of the RNA world, or the underground alchemy of the deep earth pressure cooker. Drop your thoughts in the comments, and if you're hungry for more deep dives into space's greatest mysteries, hit subscribe. Because the universe's secrets don't end here, they're just getting started, and the next big discovery, it might come from